All right, welcome to the Chapter 21, Lecture 1 pre-lecture video. In this video, I'll be giving an introduction to aromatic compounds and what that means. And so by the end of today, you should be able to use the heats of hydrogenation to quantify the additional stability of aromatic molecules versus non-aromatic molecules. You should be able to predict which molecules are aromatic and predict what molecules are anti-aromatic. And then finally, a last little point to add here, we're going to touch on nomenclature for these molecules. And so you may have noticed throughout the class that we've had sort of a special attention to triene compounds that are in a cyclic structure, such as the molecule benzene shown here. We see 3 consecutive double bonds in a ring structure. We may not know why that shows up so much, whereas other consecutive double bonds, such as hexatriene, are quite rare for this class. We don't really draw them that often, but you'll see benzene, or more often, you'll see us substitute something with a pH, meaning phenyl. An example of which would be allyl phenyl ether shown here, the Cope rearrangement from last chapter. Or sorry, Claisen rearrangement from last chapter. And so today we're going to talk about why these cyclic trienes and other related molecules are so overrepresented and why they're an important class of organic molecule that has just been popping up again and again and again in this class. In future lectures, we'll move on to the unique reactivity of this privileged class of compounds. So why are cyclic trienes, such as benzene, much more common than, say, linear trienes? Well, it turns out that they're much more stable. And you may remember from chapter 20, we used heats of hydrogenation to quantify differences in conjugated system stabilities. How that when 2 alkenes are next to each other, their stability is greater than the sum of their parts. And so what we can compare here is the hydrogenation energy. That is the energy given off when a cyclohexene is hydrogenated to cyclohexane. Something like this. So all we've done is add hydrogen across of it. And this energy gives us an idea for how stable that double bond is. We would expect the energy of hydrogenation for something that has 3 double bonds then to be approximately negative 360 kilojoules a mole. So just negative 119.7 times 3. However, if we hydrogenate a molecule called benzene to cyclohexane, it is not 3 times that. We give off far less energy, only negative 208. And because it gives off less energy, this means that benzene is more stable. The higher energy a starting material is, the more energy it'll give off if it reacts. And so there's this energy gap we have to explain. Somehow 3 cyclic alkenes together are more stable than a single one divided by 3. Again, we would expect the energy of hydrogenation to be 3 times that of cyclohexene, since we're just doing it 3 times. 1, 2, 3 double bonds. But it's much less energy given off. And that energy difference is called resonance energy. And it's due to a difference. It's due to a molecular orbital phenomenon in which having 3 consecutive is much, much more stable. This is not just something that you observe with benzene and benzene only. There are certain rules that lead to this extra stabilization. And this extra stabilization means that these molecules pop up in organic molecules we encounter in everyday life more often than you'd expect because they are themselves more stable. And so this is not a small amount of stabilization energy. This is an enormous amount of stabilization energy, 150 kilojoules a mole. This is approximately 40 kilocalories a mole, or 38 kilocalories a mole, if that's a number you're used to thinking about. So again, when we place them all in consecutive order in a flat ring structure with these 3 consecutive pi bonds, molecular orbitals arrange in such a way that they get even more energy than we would expect. So this is called aromaticity. And the rules for making aromatic molecules are as follows. They have to be cyclic. Okay? They have to have a p orbital on each atom of the ring. So if we go through and look through some of these molecules below, we might realize that, hey, wait a second. We don't have a p orbital on this carbon here with the red asterisk. This is not aromatic. We would see the similar thing for this molecule down here. We have two CH bonds implied there, not aromatic. Same thing for the cyclopropene, not aromatic. We might go over and look at this lone pair here, and we would say, is this a p orbital? Yes, because it can resonate throughout the ring. So to resonate, it has to be of p symmetry. So something like this anion here might be aromatic if it satisfies the rest of our rules. Let's take a look to see if it does. So moving on, it must have overlap of all p orbitals in the ring, planar or nearly planar. Okay, so non-planar molecules are not aromatic, and non-planar pi systems, I should say. And then finally, it has to have 4n plus 2 pi electrons. Okay, we'll talk about what that is, and it must be in a closed loop. So all of these other molecules shown on the page are aromatic. And I'll leave it to you to work through them to see why it is they're aromatic. So that is a thing I would stop and pause and see if they obey all 4 of these rules. So let's talk about the most confusing of these, the 4n plus 2 rule. N is any integer, 0, 1, 2, 3, 4, etc. It can go up to infinity. You can have an infinitely large aromatic molecule as long as the number of pi electrons fits this 4n plus 2 rule. So let's just go, for example, let's say n equals 1. If a molecule has 6 pi electrons in a cyclic flat arrangement with consecutive connectivity, it is an aromatic molecule. So if we think about that for a molecule like benzene, each pi bond in benzene is 2 pi electrons. So 2 pi, you can see where this is going, 2 pi, and so this equals 6 pi electrons. Benzene is aromatic. It obeys the 4n plus 2 rule. It's flat, it's cyclic, and all the pi orbitals are in a consecutive order. That is, they are completely adjacent. So I'll scratch out the previous examples that we decided were not aromatic because they do not have consecutive pi bonds. Let's work through one of these, such as naphthalene. Okay, naphthalene is this molecule in the green box. We can count up the number of pi electrons, 2, 2, 2, 2, 2. So that's 10 pi electrons. Does 10 pi fit the 4n plus 2 rule? It does for n equals 2. And n is just an arbitrary integer. It does not relate to the structure necessarily. It is just that molecules that have 4n plus 2 can, pi orbitals can fit this special molecular orbital arrangement that allows for this extra resonance stabilization. All right, so 10 pi is an allowed thing for n equals 2. Again, the 2 is not related to the structure of naphthalene. It is just a consecutive series of allowed aromatic pi systems. All right. And so I'll leave the rest as examples that you can work through. However, to be aromatic, it must fit this 4n plus 2 rule. Let's talk about 2 particularly confusing cases of aromatic molecules. Both pyridine and pyrrole, this molecule on the right is pyrrole, are aromatic. And if we look at nitrogen, we see that it's neutral. We'll see that nitrogen therefore has a lone pair in the ring system as the pi bonds. This lowers its energy. We have an orbital diagram here. This is the lone pair. And if we add up the total number of electrons in the pi system, we have 2, 3, 4, 5, 6. 4 times 1 just plus 2 equals 6. It's flat, planar, cyclic, and they're all in a consecutive fashion. It's aromatic. Okay. However, we don't just count every single lone pair on every single atom that's part of the ring. The lone pair has to be of pi symmetry, and it has to be inside, or it has to line up with the other rings. It has to be in the same plane. And so if we look at this lone pair on pyridine, because pyridine is, the nitrogen in pyridine is neutral as drawn, it's implied by its structure, we know that it has a lone pair. However, this lone pair is not in the pi system of the ring. This lone pair is at a 90-degree angle, okay? And so we don't count this lone pair. It has to be in the same ring. Over here with pyrrole, it's implied that it's in the same ring. With pyridine, it is not in the same ring. So is pyridine aromatic still? Well, yes, it is. We have 2 pi electrons from this one, 2 pi here, 2 pi. These are both 6 pi aromatic molecules. However, we have to be careful about how we count lone pairs. So what happens if a molecule doesn't have 4n plus 2 pi electrons, but it fits all of the other same rules? Well, there's a concept called anti-aromaticity, okay? Anti-aromatic, emphasize here, are particularly unstable. They are the opposite of aromatic. The molecular orbitals line up in such a way that they are less stable than a normal triene. It's not just the same stability as a triene, they're extremely unstable. In fact, this molecule right here, cyclobutadiene, can only be isolated in really low temperature argon matrices. It likes to do weird things like dimerize and polymerize. So anti-aromatic molecules are also cyclic. They also have a p orbital on each atom of the ring. They have overlap of all p orbitals in the ring system, planar or nearly planar. And they have 4 pi n electrons in a closed loop. So they have all the same properties as aromatic, except for the number of pi electrons. Okay, so I'm going to say you don't have to memorize a bunch of different rules. You just have same as aromatic. However, right here is where they're different, not the same. It's a different rule. So let's take a look at this molecule here below. If it's planar, if cyclooctatetraene is planar, and it is cyclic, we know that. It has p orbitals on each atom of the ring. We can look here, p orbital, p orbital. Each spot, there's a p orbital. They're all consecutive. And if we look at the number of pi electrons, 2 pi, 2 pi, 2 pi, 2 pi, that equals 8 pi e total. This is anti-aromatic. All right. So we can look at something like pyrrole. We just decided that this is aromatic. It fits 4n plus 2. So pyrrole is aromatic. It's not part of the anti-aromatic thing. The rules are still the same in how we count the pi electrons. Okay, let's look at cyclobutadiene, this molecule here in yellow. 2 pi, 2 pi. Does that fit the 4n pi electron rule? Yes, 4 times 1 random integer equals 4. 4 is the number of pi electrons it has. So this is anti-aromatic. I'll leave the rest to you. All right. So moving on, we can emphasize this. It's the anti-aromatic pi systems, again, are 4, 8, 12 are the common ones. I suppose that technically 0 pi electrons in a cyclic ring structure would be anti-aromatic. However, that's just sort of an unlikely scenario. It'd have to be all sort of empty p orbitals from boron and carbocations and so forth. So 0 is a pretty unlikely integer. However, 4, 8, 12, 16 pi electron anti-aromatics are also the more common ones. Again, there's no limit to the number that n can be. However, just due to current sort of synthetic and molecular sizes, it's usually either 4, 8, 12, or 16 pi electrons form anti-aromatic molecules. So aromaticity and anti-aromaticity are important concepts. Aromatic molecules are overrepresented. They're really common because they're more stable. Chemists can handle them. Anti-aromatic molecules are extremely rare. In fact, looking at 2 of these anti-aromatics, I know that this one, cyclobutadiene and cyclopentadienone, are both anti-aromatic. And they are not isolable. That means you can't isolate them at room temperature. They do other reactions. You have to stabilize them in other ways to isolate them. So anti-aromatic molecules are underrepresented in our organic world that we live in. Aromatic molecules are overrepresented. There are aromatic amino acids. They're an incredibly important class. Phenylalanine, tryptophan, tyrosine are important aromatic amino acids, and they're more stable than a corresponding triene. So there are certain rules for nomenclature of aromatic molecules. I want to touch on a few of these. You will not need to know exact nomenclature, but you need to be familiar with a couple rules. It'll make your life a lot easier when I'm talking about these molecules. So there's sort of an old school naming convention called ortho, meta, or para. These bromines are ortho to each other. These bromines are meta to each other. And these ones are what's called para. Okay. Six atom aromatic compounds are incredibly common. We talked about one of them, pyridine. We talked about another one, benzene. So this nomenclature is kind of specific to 6-membered rings. But what is not specific is a much more rigorous naming convention where we say they're 1, 2 or 1, 3 substituted. And so that comes from just naming or giving atom labels to the positions of the aromatic rings. 1, 2, 3. So we could say that's 1,3-dibromobenzene. Or 1,4-dibromobenzene. I'll try to use the number convention because it's slightly more rigorous. However, I may say para or meta or ortho. You need to know what those are. They're still common enough terms that they will pop up potentially on exams, so know them. Ortho is when they're next to each other on a 6-membered ring. Meta is when they have a space between them, a 1-carbon spacer. And then para is when they have a 2-atom spacer between them. However, the ortho-meta-para naming convention isn't just for things that are the same, like a dibromo or dichloro. It can refer to anything. So on the left here, we have a molecule aniline. Okay? Aniline is an aromatic molecule with a nitrogen outside of the ring. Another name for an aniline that has a chlorine on it at the 3 position, 1, 2, 3, 4, 5, 6. Or sorry, I should name them 1, 2, 3, 4, 5, 6. This could be called metachloroaniline because aniline is an aminobenzene. And meta to it, if we have a chlorometa to it, it's got a 1-carbon spacer. We can also call this 1,chloro,3-aminobenzene or 3-chloroaniline. All of these are terms you might see out in the literature. So you need to be kind of familiar with all of these. I say this because I will talk about these molecules as we discuss their reactivities, and I might say something like meta-substituted. I might say something like 1-chloro,3-aminobenzene or even just 3-chloroaniline. So you need to know what is meant by ortho, meta, para, and you need to know what is meant by 2, 3, or 4 substituted. We'll talk about this a little bit more in class, as well as the chemistry of phenols. a specific type of aromatic that is important in a variety of biological reactions as well as pharmaceutical drugs.